Hello and welcome to our next set of stats notes. We're continuing chapter 3. This is our last section from chapter 3. So far in chapter 3, in 3.1, we kind of introduced the idea of measures of center, numbers like mean, median, mode that tell you about the middle or the typical value of a set of data. And then 3.2, we talked about measures of variation, the spread of the data, things like range and standard deviation. We can measure how things are, or how spread out the data is. This next section, 3.3, we're going to talk about measures of relative standing, and then one of the ways we graph these, which is a box plot. Now, relative standing means how numbers are in position related to other numbers in the data set, whether it's how far away they are from the mean, or what percentage of values are above or below. We're kind of looking at their position within the data set. That's what this next part is. So the first thing we're going to talk about is the z-score. And z-scores are really important. We'll actually work a lot with z-scores throughout the semester. The z-score is a way of kind of measuring, a way of measuring the distance of a number from the mean in terms of the standard deviation. So it gives the distance from the mean in terms of standard deviation. So the further a number is, the bigger this value will be. If it's on the negative side, it'll be a negative value. If it's less than the mean, if it's below the mean or more than the mean, it's going to be a positive value. And this will depend on the standard deviation. So the higher the standard deviation, the more the spread. That's going to change the value of this number. Now, the way we calculate the z-score is going to be by doing this calculation. These are the same thing. One's just for the sample and one's for the population. So we can just look at the sample version. So the sample, we take the value, x is going to stand for the value we're looking at, so one specific number from our data set. We subtract the mean, so this is the sample mean, so we subtract the mean, and then we divide it by the standard deviation. And that's how we find z-score. So z-score is the value minus the mean divided by the standard deviation. So let's just show an example of this. I think it makes a lot more sense when we're actually working examples. So say we're looking at a set of numbers where the mean is 45. So that's the average, that's the middle, 45. The standard deviation is 5. So that's the spread of these numbers. They have a spread of 5. We want to find the z-score for 55. So 55 would be our x. It's the value we're working on. The mean, again, is going to be our x bar. That's our mean. And the standard deviation, that's going to be our s. So to find the z-score for this, we're going to take the value 55, we subtract the mean 45, because that's getting the distance. Remember, you subtract numbers to find their distance. So 55 minus 45 is finding the distance between these two numbers. But then we're going to divide it by 5, because we're going to figure out what this distance is in terms of how many standard deviations it is. So if we do 55 minus 45, I get 10, right? So I get 10 divided by 5, I get 2. So the z-score for this is 2. That means that this number 55 is 2 whole standard deviations above the mean. And that makes sense, right? If you take 5 and add it to that mean of 45 twice, right? 45 plus 5 is 50, plus 5 more is 55, you reach the number. So this z-score is telling me how many standard deviations, how many of these 5s you are above the number. We like z-scores in statistics because z-score gives a way of comparing sets of data that are very different. So if I always think about weights with this example. I think about how if you have weights of adults, there's a lot of spread there, right? You have adults that weigh a couple hundred pounds. You have adults that weigh only like 80, 90 pounds. It just depends on the adult. But when you have babies, there's not a lot of spread, right? They might weigh 12, 13 pounds, and that's a pretty big baby, down to like 5, 6 pounds, and that's a pretty small baby. But that's not that much spread, right? 5 to 13 pounds is a pretty small gap compared to these adults that have hundreds of pounds in difference in spread. So you can use a number like the z-score and say if that baby has a z-score of 2, then they are way above the average weight for a baby because they're 2 whole standard deviations above. Even though they're pounded to their actual how many pounds they are above average, it's not that many pounds compared to an adult that's above average weight. The adult that's 2 standard deviations above average weight is going to be way more pounds high. But this 2 kind of gives us a measure. It says, okay, this is pretty high. There are 2 whole standard deviations above the average or the normal. That's what this 2 is telling us. Okay, let's do the other ones just so we can practice this z-score method. So I want to find the z-score for 30. So for 30, that's going to be our value. So we're going to take 30, and we're going to subtract the mean. So we're subtracting that 45. and then divide by the standard deviation 5. Well, 30 minus 45, that actually gives me a negative, right? 30 minus 45 is negative 15 divided by 5. So the z-score for this one is negative 3. So this one shows us that this value is actually way below average. It's 3 whole standard deviations below average, which makes sense. 30 is 15 below 45. So if you go down 3 5, that's going down 15. That's why this is negative 3. So a negative z-score, again, a negative z-score tells me that you're below average. So if you're on weight, this would be like below average weight versus the first one would be above average weight. That's the difference. So negative 3 is way below. It's 3 whole standard deviations, so this would be really, really low. Let's do the last one here. This one's 45, which looks familiar, right? Because 45 is the mean, isn't it? So you notice when we do 45, we'll take the 45 for our value, subtract the mean, which is 45, and divide by the standard deviation 5. Well, when you subtract those 45s, you just get 0, and 0 divided by anything is still 0. So this standard deviation is 0, and that's always true for the mean. Because if you are average, well, then your z-score is 0 because you are average. You are exactly in the middle. This is the person that's not above or below the average weight. They are exactly the average weight. They are the typical value for this set. So not below or above average, they're exactly average. So this is always true for me. Okay, we're going to have one more question. This one is kind of going a little bit backwards. So instead of giving the values and finding the z-score, this one's going to have us go backwards. So we say that a data value is significant. Remember I said this in the previous set of notes, that it's significant if it's 2 or more standard deviations from the mean. So we said 2 above or 2 below. If you go out 2 standard deviations like that first one, that's where you hit the significant level. So if something's significant, it's different, it's unusual. Okay, for a data set with a mean of 70, so our mean in this case is 70, and a standard deviation of 12, so that's our standard deviation, determine what values would be considered significantly high and what values would be considered significantly low. So we want to figure out when things are significant, important, unusual. Now, significantly high means that you're going to have a z-score of +2 or bigger, right? So if you have +2, +2.5, +3, then you're significant. You're way out there. You're more than 2 standard deviations above the mean. Significantly low is going to be a z-score of -2 or below. So -2, -3, this would be significantly low because it's -3. So we want to find values that have those z-scores. So we're going to go back and we're going to use that same formula we just used. But now instead of finding the z-score, we're finding the x value. We're trying to find the data value. So we're going to plug in the information they gave us. They gave us the z-scores we're looking for, the +2, the -2. We're talking about significantly high and low. The mean they gave us, they told us is 70. And the standard deviation they gave us, they told us it's 12. And we're going to plug those in the equation. So we're going to have the z-score, +2, is equal to the value we're looking for, minus the mean of 70, divided by the standard deviation of 12. And we'll use that to figure out what value is going to be significantly high. It's going to be 2. And anything above that value would be still significant, right? Because anything more, higher, further up, is going to be, significant as well. To do this, we're going to go ahead and solve this. First off, we're going to just multiply both sides by 12. Because there's a little bit of algebra here. We're going to undo this division by multiplying, right? So multiply by 12. So I get 12 times 2, I get 24. Equals x minus 70 because I got rid of the 12. I'm going to add 70 to both sides. So I'm going to add 70 here, add 70 here. So I get rid of this minus 70. And we get 94, and we see that any value 94 or higher is going to be significant. So greater than 94 or equal to is significantly high. So that's what we'd say on that one. Okay, anything 94 or above, that's so high that it's going to be at least 2 standard deviations out there. It's going to be significant. We're going to be careful about that now. Okay, now we're going to do the same thing for low, but now instead of having equal 2, we're going to have to equal -2 because now we're looking for low values. So we want the negative stuff that's going to be a low z-score. So say -2 is equal to x minus 70 over 12. And again, that's the mean. The x bar is the 70. The standard deviation, s, is the 12. And the -2 is because we're looking for significantly low. Stuff that's more than 2 below. Okay, so I multiply both sides by 12 again. It's going to be the same process basically. We're going to multiply both sides by 12. Cancel that 12. 12 times 2 is 24. It's still a negative. X minus 70 because the 12 is canceled. I'm going to add 70 to both sides. Add 70 here, so get rid of this thing. Negative 24 plus 70 is going to be negative 46 of doing math right. 46, 60, yeah, it looks like negative 46 is what x will be. And again, this is where we want to be low. So we're looking for numbers less than or equal to negative 46. That's when it's significantly low. So those numbers are so small, we think that's kind of unusual. That's weird. Again, we don't expect much values more than 2 standard deviations out. So you can use this formula. If you have the z-score, you can go back and kind of find the values that are the cutoff. And z-scores, again, it's all about measuring how far stuff is in terms of the standard deviations. So in this case, because the standard deviation is 12, the spread is, 12 is the measure of the spread. We're talking about going out 12 twice. So I'd take that mean 70 and go up 2 standard deviations or down 2 standard deviations. Go down, up 12 twice or go down 12 twice, and that's where these cutoff points are. Okay, so z-score, it's an important number. We'll spend a lot more time the rest of the semester on z-score. Another way to measure how numbers relate in a data set is percentiles. Percentile, you've probably seen percentiles before, especially if you're a parent, you've seen these. I've got a parent, I'm a parent, I've got a 4-year-old. We do that yearly health checkup thing. We always get measurements of like height and weight and stuff, and they tell us the percentile. That's what the percentile is. It's what percentage of the group they're studying overall is below your kid or your data values value. So if your kid comes back in the 60th percentile for height, that means that 60% of students of other kids that they test are below your kid's height. And that's what a percentile is. So the pth percentile, this is just the generic way of writing it, it is a number. It's the value, the data value. It has the bottom p percent, so p percent below it, and the top 100 minus p percent above it. So for example, the 80th percentile is going to have 80% below, and the rest of the value 20% above. That's why they do 100 minus p, because if you have 80% below, then well, what's 100 minus 80 is 20. That's how much is left over to be above. So if your kid is an 80th percentile for height, 80% of kids tested are below their height, and the other 20% are above their height. That's where they drop into that range where there's only 20% are taller than them, the rest of the 80% are below. You can find, if you have the if you want to find the percentile, if you know the data value and you're trying to find the percentile, you can find the percentile by taking the number of values less than your value, divided by the total number of values, so you divide, and multiplying by 100 because this is going to give you a percent, and that's how you find the percentile of your value. So this 100 here, this multiplying by 100, that's just to make a percent. That's why they multiply by 100. So if you just divide this, you get a decimal, but if you multiply by 100, you get a percent. So the number of values less than your value, and then divide that by the total number. So for example, you have a set of data with 40 values in it, and 82 is one of the values, and it's the 13th value when they're in order. They have to be in order for this to work. What percentile is 82? So we're looking for the percentile, right? We're looking for the percentile. We know the number of values less. Now, since 82 is the 13th value, how many are less? Well, that means 12 are less, right? Because this is the 13th number. So there are 12 less than 82, because it's the 13th number as a sequence. And then since there are 40 values total, this would be your n's, the sample size, how many values there are total. Then you divide by 40, and don't forget to multiply by 100 to make it a percent. So that's how we'd find the percentile. I'd take 12, divided by 40, and then multiply by 100. And you can see that that would be the 30th percentile. So this tells us that P is going to be 30. So 30% of values below, which means, of course, because if you take 30 out of 100, you get 70 left, the 70% are above. So this value 82, because it's the 13th in order, it's not in the middle, right? 40 numbers, 20 would be closer to the middle. This is lower than 20, so this is in the lower end. It only has 30% below, but the other 70% are above. That's the 30th percentile. Now you can go backwards. Say you want to, you have the percentile, but you want to go back and find the data value. So we're going the other way around. So you know the percentile and are looking for the data value. Then we use this formula here. So we're going to take a k value, divide it by 100, and multiply by n, where k is the percentile. So K is the letter we use for the percentile. N is the number of values. So in the last case, it would have been our 40 because that's what we had. And L is going to be the answer, is going to be the data value's location. So it's going to tell us where the data value is. That's what L is. We can find the location if we use this calculation. So let's do it for this 15th percentile. We're going to find the 58th percentile of this data set. You'll notice these data values are in order. They are in order already. So if I want to find the 58th percentile, I'm going to take the percentile, K, take 58, divide it by 100, and then I have to multiply by how many values here? Well, I have 4 by 5, so this tells me that N is 20 for this data set, so I'm going to multiply by 20. So then for this, I get 58 divided by 100 times 20, and that tells me that the value location is 11.6. Now, we don't have an 11.6 number, right? Because you can't have, there's no values between. So something like this, if you have a decimal, the trick is when you do a decimal, you always round up. So if I get a decimal, it's always a decimal like this, we round up. So we would round this to 12. So the 50th percentile is going to be the 12th number. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that's going to be 73. So 73 is the 58th percentile. So if you have a decimal, you round up, and then that's your percentile. So we rounded up to 12. We found the 12th number in the sequence. So that's why 73 was our answer. It is the 58th percentile. So 73 has 58% of the data below it, and the other 42% is above. You can see how it's a little bit more than half, right? Because 58 is a little bit more than the 42 that's left over. What about another one? Let's do the 80th percentile. So now I'm going to do part B. Now, so 58, we're doing 80. We're doing the 80th percentile out of 100. We're still multiplying by 20, because there's 20 numbers in this data set. So take 80 divided by 100, and then times the 20 for the data set, and we get 16. This gives us 16. Now, what do? Do you just use the 16th? Well, actually, no. That's where you have to be really careful. You don't just use the 16th number. With this one, if your answer is a whole number, you average that term with the next higher value. So because we got 16, we'd count. We go 5, 10, 15, 16. We take this one, but we'd average it with the next higher value. So for that one, we're going to take 87 plus 88 and divide them by 2, because that's how you average, right? Add up two numbers, divide by 2, and you end up with 87.5. And it feels really weird, because you're like, why do we have to do that? It's because of the whole getting a decimal and not getting a whole number, and the rounding that happens when we do all this. So we have to go back, and if you get a whole number, you have to average it with the next one. So we end up with 87.5 is the 80th percentile. Okay, so that's a percentile. So again, percentile is a number that has that much percentage of the data below it. So now when you go to take your kid to the doctor and they say, hey, he's in the 90th percentile for height, you know they're taller than 90% of kids that they're testing. That's what that says. When they go take a standardized test and your standardized test comes back in the 85th percentile, well then that kid tested better than 85% of the other kids. That's what those percentiles are saying. When your kid comes back and they say 50th percentile on weight, that's not a bad thing. That means, hey, they're average for weight. They are right at average, because 50th percentile means 50% are below them and 50% are above. So you don't always want to be the high value, right? Sometimes you want to be the middle, or sometimes you want to be low. It just depends on what you're looking at. Percentile is the percent below. That's what you're looking at. Okay, now there are some percentiles we work with a lot, specifically the 25th, 50th, and 70th percentiles. We like to work with these because if you use those three values, you can take your data and chunk it into 4 equal-sized quarters, or pieces called quarters. So that's called the quartiles. So the quartiles, the 25th, 50th, and 75th percentiles, are called the quartiles, and by using those 3 quartiles, you can cut up your data into 4 equal-sized pieces. Here they show it for a uniform set of data. If you have a set of data that's a bell curve like this, you'll notice that the ends are going to be a little bit bigger because they're kind of, a longer piece because the data here is shorter. Here there's more data in this piece, more data in this piece, for just a little bit. But overall, this piece and this piece and this piece and this piece are all 25%. The quartiles chunk it into 4 equal size pieces. Same thing here. The quartiles chunk that into 4 equal size pieces. Quartiles, chunk that into 4 equal size pieces. I know it looks weird to say that this is the equal size, but that the same percentage of the data values will fall in this range as will fall in that range. 25% of the values are going to fall here, 25% of the values are going to fall here. So that's what the quartiles are for. The quartiles are a really nice way to take your data and cut it up into 4 equal size pieces. You can do what we've just been doing. If you know your percentiles, 25, 50, and 75th, you can just use that and find those quartiles. If you have a small set of data, there is a way to just do it by hand. So I'm going to go ahead and do that. But if you wanted to find these quartiles, you go back just like we did in the last one. If you know the percentile, I want the 25th percentile. You put 25 over 100, multiply by how many data values there are, so you can't your sample size and do that. And then you use the decimal or whole number thing. And that's how you could do it one way. The other way to do this quartiles is to take your data and find these values by hand. I'm going to do that. Now, to find these quartiles, you do need the data to be in order. So first thing you should do is put it in order, because you can't really find the middles and stuff for the 25th, 50th, 75th if it's not in order. So I'm going to rearrange this. I'm going to start off and say, okay, I think 3 is the smallest number. Hopefully I don't miss any. So we'll say 3 is the smallest. And then 5 looks like the next one. 6 and 6 are both small. There's 1, 2, 3, 4 sevens. 1, 2, 3, 4 sevens. Looks like I have 1, 2, 3 eighths. 1, 2, 3 eighths. There's a 9. Looks like I have 11 and 12 left. So I'm going to do 11 and 12. Okay, I put my numbers in order. Now, one way to find these quartiles is to actually find the median. Remember, the median's in the middle, because the 50th percentile is the same thing as the median. The median is the middle number, so that you have half the data above and half the data below. So the 50th percentile is the median. So the first thing I'm going to do the cover-up method, and I'm going to find the median this way, because by doing this, I'll find the value that's halfway between. I think it's these two, right? So 2, 4, 6, 2, 4, 6. So I can say that my median, I'll make sure I did that right, 2, 4, 6. My median is going to be in between these two numbers. So my median, halfway between 7 and 7, well, that's still 7. That's going to be Q2. Then to find the other quartiles, Q1 and Q3, well, the Q1, 25th percentile, if you take the bottom half of the data and find the middle of that, you found the 25th percentile, right? Because this is half the data, so half of that is going to be a quarter, right? Or 25%. So what I'm going to do is since this 7 didn't get used, this 7 between those. I'm going to use the bottom 7 for this set. I'm going to cover up. I'm going to do 7 and 3, 7 and 5, 7 and 6. And I'm going to say this guy is going to be Q1. Because it's the 25th percentile, so 25% of the data should be below, and 75% of the data should be above. Last one, we're going to do the same thing on the top side. We're going to cover up here. We're going to have, you have our Q2. Well, now we're going to take this top set, and we're going to cover up, cover up, and cover up until we get, make sure I did that right, that 8 is Q3. So if you have a small set of data, if you don't have a lot of values, this is a completely legitimate way to get your quartiles. You could use the formula like we saw on the last page. So if this isn't working for you, you can go back and use the formula on the previous page. But if you have a small set of data, just put an order and you can find those 3 values, Q1, Q2, Q3. Again, these are quartiles. So this has 25% data down here. There's going to be 25% of data between these 2 values. There's 25% of data between those 2 values. And then there's 25% of the data up here. So you can see that, right? There's 3 pieces there, 3 pieces there, 3 pieces there, and 3 pieces there. So these little quartiles cut it up so that all the pieces are the same size. That's quartiles. Again, each one cuts it up. Now I got 25% data in each chunk. Okay, now these quartiles are really useful, and a lot of times we'll use them with the minimum and the maximum to make what we call the 5-number summary. So the 5-number summary, it's the quartiles plus the smallest value and the largest value. That's the 5-number summary. We always write this in increasing order from smallest to biggest. And what this gives us is it gives us a nice way to look at all the different values and their locations related to each other, how spread out they are from each other, that kind of thing. So we're going to take this number set. We're going to find the 5-number summary. Now, first off, again, because it's not in order, we're going to have to put it in order. It's so mean of me to keep giving these sets not in order. It could make my life a lot easier if I just put them in order in the first place. But if you have a number set not in order, first thing you should do, always put it in order. So we got 1, 3, 4, 5. But now you have no excuse. If you're doing the homework and you get it wrong because you didn't put it in order, I showed you what you have to do, so hopefully you'll remember. Put it in order first. 6, so 3 of them. We got 8, and 13. Okay, now it's in order. Again, we'll look for the middle numbers. I'm going to do my cover-up method. 13, 1, 8, and 3, 6, and 4, 6, and 5. So these two numbers are in the middle. So my Q2 is going to be halfway between 5 and 6. It's 5.5. If you don't trust me, you can add those up, divide by 2, you get 5.5. Look for my other numbers. So on the bottom here, I'm going to say, okay, cover up. 4 is Q1. On the top side, I'm going to cover up. I'll say 6 is Q3. And then again, we use the min and the max. So I'm going to go ahead and say this guy right here is the min, smallest, right? 13 is the max. So the 5-number summary, for this set would be 1, 4, 5.5. Use this guy, not the, that's between 6 and 13. That's the 5-number summary. The 5-number summary, it's a set of numbers that kind of tell you about the data. So you can see what the smallest and the highest values are. So everything's between 1 and 13. In between each pair of numbers is 25% of your data. So the 25% of your values are going to be between 1 and 4, 25% between 4 and 5.5, 24% between 5.5 and 6, and 25% between 6 and 13. It actually tells me a little bit about the spread. You can see how between 6 and 13, this is more spread out. Between 5.5 and 6, it's pretty close together, right? That's not very spread out. So you can look at this 5-number summary, and you can think about the spread of the data, how the numbers relate to each other, where the middle is, all that's shown. It's a really good way to look at data. In fact, it's so good that a lot of times we'll graph this. That's where we talk about box plot. So a box plot is just a graph of the 5-number summary, also called the box and whisker plot. So the way you make this is you graph the minimum value, the quartiles, the Q1, Q2, Q3, and the maximum value. Graph them all on a graph. At the min and max, I'm going to put in, usually a vertical line. I think this picture I have uses an X, but usually we'll use a vertical line. At the lower, median, upper, also we'll have these vertical lines. And then we'll box the median, the middle 3 values for the quartiles. We'll box the quartiles, and we'll just put whiskers connecting the min and the max. The reason we do this is because this value right here, from here to here, is 50% of the data. And it's kind of the more important, significant percent of the data because it's kind of the middle 50%. It's not the extreme values because on the ends you're going to have the extreme values, the highest and lowest. It's the kind of the typical. So this box in here, these are the values I'm going to really expect to have. These numbers are in the middle. The values on the end are kind of the less expected. But then you can also look at things like, the bottom half. This is the bottom half of the data, right? Versus this is the top half because the median cuts it in half. So there's 50% from this range and 50% in this range. So that happens. You can see that, where it's more spread out, where it's tighter together. So you can see how this is more spread out and that's closer together. All that can be seen by looking at this box plot. So it's a really handy thing to show. A lot of times if you want to show the spreads of and compare different data sets, if you look at like multiple questions on a standardized test, they'll use box plots. If you want to look at weights between different countries, students in different countries, or heights between kids in different schools, all kinds of different things, you can use box plots to kind of show all the spreads and information. It's a great way to do that. So let's draw a little box plot with the data we just got up here. So if I make myself a number line, let's make this number line go from 0 to 15, so all my numbers fit. So let's say, okay, if I go by 3, let's say 3, 6, 9, 12. Okay, those are not very spread out. Okay, but we'll say that 3, 6, 9, 12, 15. Okay, I want to graph this. I'm going to have a value at 1, because that's my minimum. So there's my minimum, 1. I'm going to have a value at 4. So at 4 I have a value, which is going to be like here. So this is my Q1, my first quartile. That's 4. My value at 5.5, which is actually right here. So this is going to be my Q2, and 5.5. I'm going to value at 6, so that's actually right here. That's Q3. And then I'm going to have a value at 13, which is all the way over here. This is going to be the max, 13. And then, again, we box the quartiles. So we make a box around the quartiles. So that box right there contains 50% of the data. The rest of the data is going to be like that. So I just connect with whiskers to these outlying values. So again, this box plot shows me that right now I can see there's a lot more spread of this top quarter. There's the rest. And that kind of makes sense, right? Because if you look at your numbers, between 6, 8, 13, there's a lot more spread here. 13 is looking like one of those outliers. Remember we talked about outliers, and there was a way outside of our typical range. It's probably an outlier. And that's why it's making this end look really spread out, because that 13 is so big. So the box plot kind of shows that. It shows the spread of the data, how it's way more spread out here, but down here it's close together. And the box plot's showing all that. Okay, last page. Almost done with the set. Okay, so we're going to use our calculator. You can actually graph box plots with your calculator. So we're going to do that with this one. So I've got this number, so I'm going to go ahead and put it in my calculator. I did cheat and went in ahead of time. So remember, hit the stat button, hit edit, and there's where you can enter data. So I did type that in ahead of time. I went in there and just typed in my values. You type my 43, hit enter, type my 57, hit enter, until I got all the values in that data set. Okay, once you have them in this data set, you can get both the 5-number summary and the box plot from your calculator. So I'm going to have this data. This will be list 1. And I'm going to do the 1-bar stats. We'll do these 1-bar stats a lot, so hopefully you're familiar with them. You're seeing how this is important. So hit stat, go to calculate, and then there's 1-bar stat. Make sure it's still saying list 1 if this is in your list 1. And then calculate. And the information we need, the min, the max, all the quartiles, it's at the bottom. So you just have to scroll down. And at the bottom you can see there's the minimum, the Q1, which is the quartile 1. Median, remember the median is Q2, Q3, and the max. So all the information we need is right there. Isn't that awesome? So if you put it in your calculator, it'll give you the 5-number summary. No problem. You don't have to do that yourself. Just do the calculate, the 1-bar stats with list 1. And so from that we see the min. What was the min? 29. Q1 was 57. The median, or Q2, was 87.5. The Q3, upper quartile, is 118. And the max is 215. So that's the 5-number summary. Just, that calculator just gave us the 5-number summary because we put the data in there. Now to get the box plot, draw the box plot, do that in the calculator. What you'll do is you'll go to the second stat plot. So we need to use the stat plot. If yours is still on, that's great. I've been using mine for algebra, so mine's off. So I'll hit enter there. The first thing I'm doing, I'm going to make sure and turn it on. So I hit enter to turn it on. And you'll see down here, there's actually 2 different box plots that we have. We're going to go with the one that this is the last one, not the last option, but the last box plot, so the second to last graph. That one's going to be the regular box plot, so we're going to hit enter on that. X list is just our list that we have in there. We don't need a frequency list for this one because we didn't put a frequency in. We didn't have a list of how many of each. So I'm just going to delete that. And then I should be able to graph that. Oh, nope. Okay, you can't delete it. I was remembering wrong. I was sitting there, I was trying to remember if it was delete it or if you do just put a 1 in. I think you just put a 1 in because you want all of them to show up once. Now it should graph. Yeah, that's what it was. Okay, sorry. Put a 1 in there and then it should work. Now, it doesn't graph very nicely right now because it's not zoomed for statistics. If you have yours still zoomed for stats, you might be okay, but mine wasn't, so I'm going to go back down to zoom 9. So I hit zoom and then 9, and then it will give me the proper box plot. You can hit trace on there, and it'll show you those different 5-number summary values. So you can see the min, the Q1, the median, the Q3, and the max. And so you can actually get that data from graphing it. You don't even have to use the 1-bar stats. You could actually just graph it and then look at it that way. But there you go. That's your box plot for this. So you can draw the box plot. Again, to do that, second stat plot, it's the fifth graph. Now I just want to show you real quick, if you're wondering what was going on, oh, never mind, I'm going to talk about that later, so I'm not going to jump into it. So, okay, so that's your graph using your calculator. And you could do this for any problem where you have to sit there and graph a box plot. You can use your calculator to get it. Okay, a couple more things to wrap this section up. Let's talk about the interquartile range. So the interquartile range is like range. It is a subtraction between two different values. But instead of subtracting the top and the bottom, we're just going to subtract the quartiles, the first and third quartiles. So it's kind of a range of the middle piece. Instead of being a range of the whole thing, it's kind of the range of this middle piece here. Instead of the top to the bottom, the whole thing, it's just the middle piece. So we can find that. We can find the interquartile range, also called the IQR for short, because who wants to say interquartile range all the time, by just subtracting. So for this setup here, we'd say Q3 is 118, Q1 is 57, and we just subtract those, and that would give us the interquartile range. So 118 minus 57, and we see that 61 is the interquartile range. So 61 is your IQR. So be ready to find the IQR. Again, the IQR is just the range between the Q3 and Q1, the two different quartiles, the two outer quartiles, not the median. Now, I mentioned outliers. I mentioned how we had an outlier on the previous page. So outliers do show up, and one of the ways you can kind of identify outliers is actually using the interquartile range. So we say, data values that are really outside and really far out, towards the end, are probably outliers. And the way you can check that is you can say, if they are beyond your lower or upper limits, lower if you're on the bottom, upper if you're on the top, then they are probably outliers. So you find a lower limit by taking Q1, so the lower quartile, and subtracting 1.5 of your interquartile ranges. You find the upper limit by taking Q3, the upper quartile, and adding 1.5 interquartile ranges. So let's do that for the previous problem. So let's first off find our lower limit. Find our lower limit, we're going to take our Q1. So in this previous problem, our Q1 was 57. So we took our 57. And we're going to subtract 1.5 times that interquartile range, so times 61. And that will tell us kind of where our cutoff is. I'm going to take 57 and subtract 1.5 times 61. And it gives me negative 34.5. So I would have to be below negative 34.5 before it would be an outlier. And none of my values, of course, are even negative. So this one I'm pretty safe. That has to be pretty far out. So that's not going to be an issue on this one. Now, if I check the top value, so if I go up instead of down to find the upper limit, then I take Q3, which is the upper value. Q3 is the 118 we have here. So take 118. I subtract 1.5 times my interquartile range, my 61. And that'll kind of give me the upper limit. That's what I do there. So 118 minus 1.5 times 61. And again, so I'm taking 1.5 of those interquartile ranges, and I shouldn't be subtracting, I should be adding. Whoops. We're going up, we're not going down, we're adding. Good thing I caught it here. Okay, so we're adding, because we're adding to go up, and I got 209.5. So any value above 209.5, I think is probably an outlier. Any value below negative 34.5, I think an outlier. And I do have a value that's above 209.5, because I have this 215 that's above that value. So we would say from this, based on this, that 215 is probably, I can't say for sure because it might still be a good value. I might not have collected enough data or anything, but this is probably an outlier. Now, if we have a number like this, so that we think it's probably an outlier, it's going to be a max or a min. In this case, it's a max. And so when we draw our box plot, we can see that that outlier is going to probably mess up our box plot because it's going to really stretch it out. So we saw on the previous page where we had that 13 and it really stretched out this side. So what people do is they actually sometimes will take a set like this, a box plot like this, and they won't use that outlier, that potential outlier. They say that number is so extreme, I don't think it's a really good number, we should probably not use it. And so they make what they call a modified box plot. A modified box plot is a box plot where you don't draw the outliers. We don't really mark them except for maybe putting a little X or a dot on them. We actually draw our lines to the next highest value. So denote outliers with an X or a dot, and we draw the line to the next highest value or next lowest value. So we want to do a modified box plot for this data up here that we just did. So to do my modified box plot, what I would do, I'd have my graph, and I would draw it, and I would put my values. We have our min of 29, our Q1 of 57. So this is just from the top of the page. Our median, which is like 87.5, which is Q2 or the median. And then we have the Q3, which is going to be 118. So let's say 118. And these aren't probably perfect. Box the middle three, connect to the bottom because that's not an outlier. But then we go to do the top, we don't connect to 215. So at 215, we put like a dot or an X, and we would actually connect to the next highest number. So the next one after 215, I think, is the 127, right? That's the next highest number. So we'd actually go over to 127 and connect to that. So this is the next highest. And this box plot is going to be a little bit better in some ways, because right now it doesn't make it feel like this top is super spread out. It feels actually a little bit shorter than some of these other ones. Versus if you include that outlier, it's going to really make that look way spread out. It's just that outlier that's doing that. Now, you can do it by hand like this, but you can actually also use your calculator to do this. So when you did that stat plot, you saw there was two different graphs for box plots. Well, the first one is actually a box plot where it doesn't use the outliers for the lines. It takes the outliers and just marks them with dots. So we're going to go ahead and do the same set. It asks what kind of mark. I'm going to just leave it as a circle for the outliers, and then we're going to graph it. And so now you can see it actually just put a circle where the outlier was instead of marking it. So if I do a trace here, we can see that that is still the max, right? That's the highest value, but it's only connecting to the second highest value. It's connecting to 127. So that's the difference. So if you want to do that graph, you can do that. Now, one thing that's really cool about this is if you're just trying to figure out what might be outliers, you can actually take any data set and graph it with this modified box plot, and it'll basically label the potential outliers for you because it'll do them separate like this. And so now you know, oh, that's potentially an outlier. So I need to be careful about that number because it might be an outlier. It might mess up my data set. So that's a modified box plot. So if you want to identify your outliers, you can do that. Now, this doesn't give you the interquartile range, so you should be able to find the interquartile range in your lower and upper limits in case you ask about those in the test. But it does help you find those outliers. Okay, so that's outcome, or this is section 3.3. So this is a 3.3 section. Again, we worked with z-scores, finding z-scores. We worked with percentiles, being able to find the percentile, or vice versa, if you have the percentile, finding the value. And then working with those quartiles, finding the Q1, Q2, Q3, and then using those to make the 5-number summary and the box plots, or the modified box plots. So that's what we covered in this section. Okay, good luck with the homework. If you have questions, like always, make sure you're using the Ask My Instructor button. I'm happy to help with stuff. I really want you to use the Ask My Instructor because it labels what section you're in. I had a person email me just the other day, and I didn't know what class they were talking about because they used the Ask My Instructor button and they didn't specify in their email. So if you specify, it helps me out. I'm usually teaching more than one class, and so I need to know which class you're working on and talking about. So, but good luck till next time. I'll see you on the next set of notes.